Welcome to the League of Women Voters presents Insights and Perspectives. I'm Jim Lathrop, your host for tonight. The League of Women Voters is a political but nonpartisan organization that believes an informed public is vital to a democracy. Tonight our guest is Elinor Gates from Lick Observatory. Welcome.
Thank you for having me.
Oh, we're glad you could come. Could you tell us a little bit about yourself, how you became an astronomer and why you did such a thing?
Well, I think I've always been interested in math and science, and astronomy is just so intrinsically fascinating. When I was a kid, I'd see all the science programs on black holes and the expansion of the universe. I thought, that is really cool stuff. And it wasn't until high school and I was looking at college, I was like, I can actually major in this in college and become a scientist in that field. And it's the interest in astronomy has never flagged, and I'm so pleased I can actually do it as a profession now.
That's great. Tell us a little bit about Lick Observatory. James Lick was quite a character, but give us a brief introduction to Mr. Lick and how the observatory got started.
Yeah, James Lick was actually born in Pennsylvania and started out as a cabinet maker's son, and so he learned to do woodworking. And he fell in love with a miller's daughter, and when he wanted to marry her, his father said, "No, you may not. You're not rich enough. You're not going to be able to support her. She was the daughter of the richest man in town." And he said, "Someday I will build a mill that makes yours look like a pigsty in comparison." And he went off to make his fortune. In that process, he became an apprentice to a piano builder and gained some more woodworking skills. And he discovered that most of the pianos he was building were actually being shipped down to South America. And so he decided he could cut out the middleman, go to South America, build his pianos, make a tidy profit. And he did. And so after about a decade, he came back to claim his bride, Barbara Snavely, but she had married someone else. So with nothing for him in the United States, he went back to South America, spent a lot of time in South America, eventually ending up in Lima, Peru, and by the 1840s decided that maybe the West Coast of the United States was going to be a profitable place to be. So he came to the Bay Area, San Francisco, in 1848, 2 weeks before gold was discovered. And he had a tidy little fortune from his endeavors in South America. And he started buying up land like mad before the gold was discovered. And then once gold was discovered, all these people coming into California were buying land to build their homesteads and mining claims and everything. And he became the richest man in California by the time the 1860s rolled around. And so he wanted a monument to himself. And so he was thinking of all sorts of ideas for how he would be remembered as the richest man in California. And one of his ideas, which I just love, was to build a pyramid bigger than any in Egypt in downtown San Francisco at the corner of 4th and Market. Luckily, one of his good friends was George Davidson, the president of the California Academy of Sciences, which James had supported by providing them a building in San Francisco as well as some funds. And he convinced them maybe that wasn't such a good idea. And he eventually settled on building a telescope, the best telescope in the world, and an astronomy department to go with it that would eventually become part of the newly formed University of California. And that's how Lick Observatory was born.
That's amazing. So you had the first major telescope in the country that's used full time. That's right?
Yeah, well, Lick Observatory, astronomers at the time knew that viewing was better from the top of a high mountain to get above a lot of the pollution and air and turbulence of the Earth's atmosphere. So mountaintops were preferable. And all the telescopes that were on mountaintops at that time were only accessible during the summer months because it was so snowy during the wintertime. And James Lick wanted his telescope, the greatest in the world, to have also the best viewing. So he wanted to be accessible year-round from the top of a mountaintop. And so Lick Observatory's claim to fame at the time was the biggest telescope in the world on the best site that they could find at the time. And today, all large telescopes sit on top of mountains because clearly it's the right thing to do for the science.
Okay. And we've got a picture of the observatory. which has, now how many telescopes are actually up there?
Well, we actually have 9 telescope domes, of which 4 of the telescopes are fully modern and used for research every night, and a couple other of our telescopes are used for education and public outreach. In fact, if we can go to the next picture, that is our historic 36-inch refractor, and this is the telescope that James Lick caused to be built. It was the largest telescope in the world of its kind at the day, and today remains the second largest telescope of its kind in the world. And this one is used not for research anymore, but for public education and outreach, and also teaching students. And so we actually have public programs where people can come up to the observatory and view through this telescope.
Oh, okay. That's when would one come up, or do you have to make an appointment to
you
use
do
that?
You do have to buy tickets. I believe our tickets for our summer program will go on sale in April. And there are about a dozen nights during the summer where you have viewing, and there are also science and history lectures, and some of those nights actually include concerts, so that you can listen to a concert before viewing through our telescopes.
I've been told by someone that they have concerts up there. They
Yeah.
still do that?
Yes, yes.
Okay.
It's called the Music of the Spheres.
Oh, that would be neat. Okay. Now, you have a 1-meter telescope.
Yeah, so
Reflector.
we have a number of scientific telescopes that are used for research, and one of them is our nickel 1-meter telescope, named for Anna Nickel, who provided the funds to build the telescope. She was a seamstress in San Francisco, so we're not quite sure why she decided Lick Observatory was where she wanted her money to go, but certainly it was wonderful because this telescope is used pretty much every night, every clear night of the year, for doing research. And some of the research topics are, say, observing supernova explosions in other galaxies. These are stars at the end of their lives blow up in these huge thermonuclear explosions. And so we track them, discover them with one of our other science telescopes, the Katzmann Automatic Imaging Telescope, and then follow up those discoveries with the 1-meter telescope.
Okay. Then you came up with a 3-meter telescope.
Right. Our 3-meter, the Shane 3-meter or 120-inch diameter telescope, is our largest research telescope on Mount Hamilton. It was built in the 1950s, and at that time it was the second largest telescope in the world. And that is really our primary research telescope. Our telescopes are available to any of the researchers in the University of California system, and that includes all the UC campuses, as well as the national laboratories, Lawrence Livermore Labs and Lawrence Berkeley Labs, that are administered by UC, and any of the researchers can use that telescope. And we have a wide variety of different instruments so that they can look at light in different ways to discover different things.
Okay. How long have you had the 3-meter?
The 3-meter was used for the first time in 1959.
So that's reasonably recent. Okay.
Yeah.
Now, the university has 2 places where they have telescopes. There's one in Hawaii. That's also University of California.
Right. University of California, or University of California Observatories, is the parent organization for all the major research astronomy facilities in the University of California, and that includes the 2 10-meter telescopes in Hawaii on top of Mauna Kea on the Big Island.
Okay.
Yeah, there are 2 10-meter telescopes, and they are currently the largest optical telescopes in the world. And then, of course, they also run Lick Observatory, and we're also involved in a third telescope project, which is called the 30-meter telescope, which they just broke ground to start construction of that telescope a couple months ago.
And that will be in Hawaii?
And that will also be on Mauna Kea in Hawaii.
Okay.
Yes.
That's amazing. Let's see. We may be about time to take a break. I'm not sure how we're doing on time. Maybe or maybe not. Okay, if not, we can keep going then. Okay. Let's see. Now, one of the interesting new developments is the thing where you can take care of the fact that coming through the Earth's atmosphere, light gets shifted and moved around. Why don't you tell us about that? That's the adaptive optics.
Yeah, so one of the problems with ground-based telescopes is that we're actually looking through the Earth's atmosphere. And the Earth's atmosphere is turbulent. It's sort of like bird watching from the bottom of a swimming pool. Everything's all ripply and moving, and you don't get very clear images. And so adaptive optics is essentially a way to measure the turbulence in the Earth's atmosphere that's blurring our images through the telescope. and correcting it in real time so that you get nice, crisp, clear images. So one of the things that's so wonderful about the Hubble Space Telescope is it actually is above Earth's atmosphere, which means that it doesn't experience any of that turbulence and blurring that ground-based telescopes do. But it's hard to put very large telescopes in space. It's very expensive. So while the images from the Hubble Space Telescope are gorgeous, you have the entire community of United States astronomers using one telescope.
Okay.
So ground-based telescopes are much more common. They're much larger. And so with adaptive optics technology, we can clean up those images and get images better than the Hubble Space Telescope with our telescopes here on the ground.
Okay, now I understand that in order to do that, you have to have a bright object near it that you know where it is?
That's right. I mean, we know that what stars look like if there's no turbulence. They're point sources. They're unresolved, okay. So you don't see any details on the stars. And so we can measure by looking at a bright star in the direction we're looking how the atmosphere is blurring things on an almost instantaneous basis. So we're measuring the blurring of the atmosphere from this bright star up to maybe 1,500 times a second. And we sort of work backwards. How's it blurred? Well, what does that turbulence look like? And then we actually have what's called a deformable mirror it's actually a thin glass mirror with little pistons on the back. With our old system, we actually have some new technology with our new system that actually push and pull on the mirror to change its shape in real time, up to 1,500 times a second, to counteract that turbulence and clear things up. But the trick is, you need a bright star in the direction you're looking. And you look up in the sky and say, oh, there are bright stars everywhere. It turns out that only 1% of the sky is near enough to a bright star for this technique to work. Now, that 1% of the sky is very interesting, but I tend to look at very faint galaxies and that never seem to have a bright star near enough for this technique to work. So we astronomers are clever and get around this by creating a fake star wherever we need one with a laser, so that we have a bright artificial star to make these same measurements wherever we need one.
That's kind of mind-boggling that you could do something like that. How are we doing on, we got a fun fact coming up. This is our idea of a commercial. So see what happens. Okay, what kind of things would we normally see that come out of your ability to do this, the adaptive optics? What have we seen in the newspapers or in Science Illustrated or any of those?
Well, I think one of the major things that adaptive optics has allowed us to do is do things like image the center of our galaxy. We think that all large galaxies have supermassive black holes at their centers. And it turns out our galaxy has one as well. So using adaptive optics at Lick Observatory and also at the Keck Observatory, once we developed it at Lick Observatory and proved it worked, particularly this laser to create an artificial star, it's been put on larger telescopes like the Keck telescopes in Hawaii. And we can look at the center of our galaxy and we can actually observe stars orbiting around this black hole. So we don't see the black hole itself, okay, but we do see stuff apparently occasionally get sucked into the black hole and stuff orbiting around it. And we can use what's called Kepler's laws. It's a very basic physical law about how things orbit to measure the mass of that black hole. And so with adaptive optics, we've been able to see enough detail and track these stars to know that the black hole at the center of our galaxy weighs about 4 million times the mass of our sun.
Wow.
So that's one thing. And this adaptive optics technology is not only useful in astronomy, but it's also useful for other things. So adaptive optics is now being used for vision science. We can use the same technology that unblurs images of stars to give us clearer views into, say, people's eyeballs and see what's going on with the cells in your eyeball and study things like macular degeneration and diseases, vision loss from diabetes and things like that, and study it in a non-destructive, safe way and see are treatments working, are they not? So these are transferable technologies. That's one of the things that people don't usually think about in astronomy, that we develop new things that might be applicable in many other fields as well.
Instead of looking far away, you can look up close in much more detail.
Exactly.
I wish I'd become an astronomer almost. Well, now you hit the news a few days ago with Google making a generous gift to you. How is that going to help astronomy out?
Well, it was really fabulous that Google gave us $1 million donation. It's $500,000 each year for 2 years, and we're hoping that they will continue that in future years, depending on how this goes. We get lots of grants from places like the National Science Foundation, NASA, to build new telescopes and instruments, spectrometers and cameras to look at the light our telescopes collect. But one of the problems Lick Observatory has been facing, is the budget cuts that the University of California has been experiencing for quite a long time. And Lick Observatory, being run by University of California, has not been immune from that. And so our operating budget is actually below what we really need for full operations of all our research telescopes. We have 4 research telescopes, and they require staff to keep them running and operating optimally. So this money from Google will actually help us hire some more staff, new telescope operators and dome mechanics, and help us hire people maybe to expand our public programs and public outreach. So this is, helping with those operational costs is just going to be a huge boon to the observatory, and by extension, the Bay Area, because one of the things Lick Observatory does is train new scientists, and those scientists, whether they go into astronomy or go into technology industries, is the future of the economy. So this is a long, it's a bigger scope than just keeping Lick Observatory running for the University of California.
So you actually have students coming in from the various campuses to
yes,
use
our facility is available to students at all of the UC campuses that have astronomy departments, and so we have students from UC Davis building spectrometers in the basement of our 3-meter dome, or we have students, undergraduate students operating the 1-meter telescope, learning how to take astronomical data and deal with modern instrumentation and the high-tech tools that we use, as well as postdocs and graduate students conducting their own research with our 3-meter telescope.
Wow. Now, tell us a little bit about what your interests are, or what you are doing.
Yeah, well, I have 2 main areas of research, and one of them is on the instrumentation side on adaptive optics and using the newest technologies to make those systems work better. And so we've just commissioned a brand new adaptive optics system on the Shane 3-meter telescope this year that give us higher resolution and improve the turbulence in the atmosphere even better than we did with our original system. And then my other thing, research is scientific, looking at quasars and the black holes at their cores and trying to measure their masses. So there are a couple different ways of doing this. One is that there happens to be a correlation between the size of the galaxy and the mass of the black hole at its core. So with these very, very distant galaxies called quasars, they're so far away that the galaxy is really, really tiny. Just for our viewing, just from our view, because it's so far away. And the core, the black hole, is sucking in so much material. As that material gets sucked in, it gets really hot as it hits the accretion disk and emits enormous amounts of light. And in fact, that very small core right around the black hole is brighter than the whole rest of the galaxy combined. So it makes it very hard to see the galaxy, particularly with the turbulence from the Earth's atmosphere. So I use this adaptive optics technology to sharpen up the images and see that that core is really a core, and see that really faint galaxy around the core. And once you can see that galaxy, then you can estimate its size and its mass, and from that make an estimate of how massive that black hole is at its core. And we actually find that around these faint galaxies, the longer you look at them, you actually find other galaxies around them. So I've actually discovered a fair number of galaxies, and discovered that most of these quasars tend to be in little groups of galaxies that are associated things nearby. So to me, it's very interesting, and trying to understand how these things have changed. So we don't see quasars near us.
Okay.
We see them only, say, 8 billion light years away from us, or earlier in the universe. And so what has changed since then, in the dynamics of the universe, that we don't see them nearby?
I remember seeing something about finding a cloud that was present at the Big Bang or something to that effect. I don't know if that was yours or if that was something else.
Well, I think that I'm not necessarily familiar with the details of that research, but certainly, I mean, we know that our universe is about 13.7 billion years old, and so the quasars and active galaxies I'm looking at tend to be about 8 billion light years away and closer. So I'm not looking quite back as far as other researchers. But you know, there's so much out there that we don't know. So there's an awful lot of the universe to explore still.
That's still doable. One of the things I noticed on your website, and I hope they've been putting your website up from time to time, but there was a thing that the observatory and the city of San Jose had worked out an agreement to kind of cut down the light, and they chose street lights that would not pollute or create light pollution that would interfere with your using them.
Right, yeah. Lick Observatory back in the 1980s worked with the city of San Jose to limit light pollution because San Jose was growing as a big city. And the lights from San Jose, you know, a lot of that light bounces off the pavement, or some of those lights are poorly designed and facing straight upward and wasting most of their energy going up into the sky where it's not useful. But that bounces off molecules and things in the atmosphere and actually makes it harder for us to see the stars at Lick Observatory. And so back in the 80s, some of the most efficient and cost-effective lighting were what were these low-pressure sodium lights. And those are the yellow street lights that people see throughout San Jose. And that was a great boon to Lick Observatory because that meant all the light was one color and we could just filter it out and everything else was good for us to view. Of course, now times are changing and they're switching to even more cost-effective lighting, more energy efficient, which are these LED lights, which are white, which I know the public really likes the white color better than the yellow street lights that I know a lot of people didn't like, even though it was so wonderful for astronomy. And we're again trying to work with the city of San Jose to potentially have them, you know, dimmed after a certain hour when there's not very much traffic, and make sure that they're in proper, what we call full cutoff lighting fixtures, so that the light is all directed at the ground where you need it, not going up into the sky and polluting our view of the sky. So, you know, while San Jose is a big city and we do have light pollution, it's not destroying our science because of working with the city. And then, of course, when we're lucky, we have the marine layer roll in over San Jose so that you're below the fog, but it blocks the city lights, and it's as dark as any place on this planet for doing astronomy when those weather conditions are just right.
So you're praying for rain and fog.
Well, we want fog at the low levels. Well, clear up top of Mount Hamilton.
Want that.
Yes.
Okay.
Of course, everyone wants rain right now to deal with the drought, but that's not so good for astronomy.
Okay. Well, tell us a little bit about what the public can see at Lick Observatory.
Yeah, well, Lick Observatory, you know, most people in the Bay Area have actually seen it, you know, because as you drive south on 101 or 280, you can see the white domes on top of Mount Hamilton, the highest peak in the Bay Area. And we are actually open to the public every day. Our 3-meter telescope, our largest telescope, actually has a viewing gallery, so you can go in and see the telescope, and there are some displays there about its history and the science it does. And Thursday through Sunday, from noon to 5 p.m., our visitor center is open so that you can drive up, look at the views of the Bay Area, and learn some more of the history and get some free viewings of the historic 36-inch refracting telescope. Okay. So it's a really fun place to visit. There's a lot of information and learn more about the history and science we do.
And you said there are times we could come up and actually look through one of the telescopes?
Yeah, so we have our summer visitors programs, which are a half dozen weekends during the summer on Friday and Saturday nights, where you can purchase tickets in advance and come up and view through our historic 36-inch refractor, as well as our 40-inch reflecting telescope, just in the same building. And we also have history and science lectures. Some of the Saturday nights also have concerts. And we have volunteers that bring their own telescopes, some of them really marvelous instruments, to share with our visitors so that you can look through a large number of telescopes in an evening.
Oh, neat. I will try and take advantage of that. Mm-hmm. So what's next? I mean, you've got a 30-meter one going in Hawaii. Will you people be involved in that, or?
The staff at Lick Observatory are not directly involved in the 30-meter telescope project construction or anything like that. But this adaptive optics system we have just put on the 3-meter telescope this year. The new one uses some new technologies that will probably be used. We've been testing them with the intent that they will be used on the Keck telescopes and potentially the 30-meter telescope in the future. So Lick Observatory, one of the things we excel at is testing and building new instrumentation using new technologies that will be then applied to the larger telescopes. And so that's one of the main things we do at Lick as well.
Okay. I noticed that one of your astronomers is now at CERN.
We have many astronomers that have been at Lick Observatory, and they end up all over the world at prominent research facilities.
I thought it was the director. Is at CERN now? No, maybe not.
It's not ringing a bell. I'm
okay.
sorry.
Maybe it was before you were there. Okay. Let's see. What have we missed that you're willing to tell us about? That we've got about a minute left, I think.
Well, I think, so it's one of the major telescopes we didn't talk about was the Automatic Planet Finder, APF telescope, which is our newest telescope on Mount Hamilton. It's 2.4 meters in diameter and fully robotic. And its sole purpose is to discover planets around other stars. So this is very exciting research. Lick Observatory has been one of the leaders in discovering planets around other stars. Most of the first 100 planets discovered around other stars were actually discovered at Lick Observatory, and that allowed us to get funding to have a telescope dedicated to this work. And it's already discovered a couple new planets around other stars since it was installed, and many more will come.
Well, there was a thing in the paper about some planets that are kind of within the habitable area of something.
That's right. We're discovering more and more.
And I'm being told that we're about through. So thank you very much for coming. And I've learned a lot, and I'm excited, and I want to go up and see what you have. So I think that should be it.
Thank you.